Okay, so let's begin. I had some questions over the weekend about section 1.8 of the textbook, which is on the syllabus, right? This is all about recognizing the graphs of quadratic surfaces, right? And these are surfaces of this form, right? Things that involve squares of our three variables, x, y, and z, corresponding to functions of two variables, right? Where z, of course, we usually view as the output. So there's an analogy here with the conic sections, right? These are much similar to, who can remind me what the conic sections are? Sorry, I just want to make sure that we're unmuted here. Yep, everything's good. What are the conic sections from Algebra 2 back in high school? You remember this? First of all, the phrase conic section means a part of a cone, right? And we usually think of it as a double cone, right? This is, say, something like this. Right? And the conic sections are ways in which we can slice these cones, right? What are the conic sections? Remind me. Yeah. Ellipse, yeah, good. That's excellent. So not only do we have circles, ellipses, parabolas, and hyperbolas, I'm really glad you said this, lines, right? The pathological conic section, when we slice the cone directly in half, we get a pair of intersecting lines. Right? Okay, so all those shapes have equations that only involve squared terms of x and y. This is the three-dimensional analog of this, right? Quadratic surfaces. These only involve up to square terms of x, y, and z, right? So instead of giving you like a formal treatment from the textbook, what we're going to do is just look at some of these. This is a really great website, right? For all these possibilities, we have, click on any of these and you get, okay, so if we, oh, sorry, when you're in the little applet, you zoom in there. So each of these links at the top gives you the general form of the graph of such a thing, right? Where the signs are either positive or negative. Yeah, so, and you can see what happens when you change, if I take a particular value of x, I get a cross section, right? Basically, when I move this slider, I'm choosing a plane, right? See these orange curves here, here, and here. I'm choosing this plane that intersects the graph of this general equation up here, right? Here, A is 1, B is 1, and C is 1. So what conic section do I get when I take a cross section for a constant value of x, i.e. a plane that is parallel to the YZ plane? This forms a conic section. What conic section do we have here? Yeah. Right, or in other words, a hyperbola, right? That's when you take a plane and slice the cone like here, right? So how about if I choose a z value before I touch the slider? What shape will I get? What conic section will I get if I pick a particular value of z and slice at the plane defined by that constant value of z, i.e. something parallel to the xy plane? Yes. Yeah, I'll get a circle, right? So let's see that illustrated. So I get nothing here in the middle, but as soon as I choose a value of z large enough, I get this expanding blue circle here, right? And when I get negative enough, I get this blue circle on the lower sheet, right? Now, if you scroll down a little further, you can see what happens. So the top example is when all the coefficients are A, B, and C are 1s. What happens if we change A? What's the expectation here? A, recall, is what we divide negative x squared by. sorry. What do we get if we change the value of A? How does the graph of this thing change, this hyperboloid of two sheets? Yeah. Depending on which way we move it, you're correct, right? If we get smaller, we twist up. We get larger. Yes, exactly right. We kind of flatten. Good. Likewise, for our other parameters, A, B, and C. C is a little different, right? This brings our sheets closer together. Okay, so you can do this for all the possible quadratic surfaces. They're all linked right up here. And let me tell you up front, I'm never going to ask you to draw a graph of a particular quadratic surface, but it will be immensely helpful to you if you have some familiarity with the different possibilities of what the quadratic surfaces are. Because this will give you an idea of when we talk about a level set or a particular cross-section of one of these functions of any of these types, then you'll have an idea of what's going on, right? So here's some homework that I recommend, but obviously we won't test or collect. Just go to this website. I'll send it out via Canvas later today and take a look at all these different shapes and give yourself some familiarity with each of these. Here's like an ellipsoid, right? Like an egg shape. And anyway, I take a cross section of this, I'll have an ellipse somewhere, right? And an ellipsoid is really just like a sphere, but it has some skew aspect of its dimensions. Right? Anytime I make these sliders all equal, I get back to a sphere, but I can make it eccentric, so to speak, that is non-circular, by stretching it one of three ways. Okay, so let me see. This is really the key example that we'll come back to quite often. So before I touch any sliders here, what will I get if I take a cross section where X is constant? Yeah, a parabola. Let's see. Yes, look at that. It's a parabola that opens down. Down. By down, I mean in the negative Z direction is how it's open. Now, what if I were to take a cross section where Y is constant? Yes. Okay, let's see what happens when we move Y. Yeah, we get a parabola that opens up, right? Okay, so with that information combined, let me organize these to be fairly close together. What happens when we take a cross section when Z is constant? Yeah, we get a hyperbola, okay? Almost everywhere, except at, yeah, great. What happens at Z equals 0? Yeah. Very close. Very close. Two touching parabolas. Yeah. Two intersecting lines. It's that degenerate conic section, right? It's when you slice the cone directly in half and you just get two lines. Let's see it illustrated. Okay, so here's our hyperbola, right? These two sections. Here it is, getting closer and closer and closer together. Wait, there it was. Right there. Becomes two intersecting lines right there. Yeah. And then we have the two pieces of the hyperbola switch orientations. It goes from this to two intersecting lines to this. Okay, we're going to come back to this particular example quite often. All right, so familiarize yourself with these shapes. It'll come in handy quite often. All right. So, good. Let's get back into the standard format here. Don't mind the fractal here. Now you get to see how inept I am at operating a camera. Okay. So, what I call correctly, we're at a place where we can start to talk about partial derivatives, right? We completed our discussion on topology at the end of Thursday last week. And hopefully you saw on Canvas that I posted some notes, just recording the basic definitions. And there you'll find some exercises just to get comfortable with what open and closed and all these concepts that we kind of breezed through. It happened very fast, right? So look for some written material on Canvas if you haven't already. Okay, good. So partial derivatives. So remember when we talked about vector valued functions of a single variable, all the definitions of differentiability, continuity, continuous differentiability transferred pretty cleanly from what we remember from calculus 1. Now we're in a quite different situation because when we talk about the derivative, we're really talking about a rate of change, right? When we consider functions of more than one variable, it's ambiguous to say what is the rate of change of this function. We need to specify what variable we are considering the rate of change with respect to, right? Ultimately, our goal is to collect all that information into one mathematical object. That is to say, we would like to record how a function changes with respect to all of its input variables at the same time. And how we will do this is by first transferring everything we know about the rate of change of a function of a single variable to each of the variables that a function with more than one variable has. So here's the definition. None of these markers are good. None of them. Let me try one more here. What does this do? Slightly okay. Thank you. Appreciate that. Okay, so next. Our definition. Let's start by considering a function that goes from R2 into R. And it's often useful to think of this as having a variable associated to the output, just like we saw with the quadratic surfaces, right? We set some equation equal to z involving x and y. Okay. Then the derivative of f with respect to x. Right. Special note of this. This is a key phrase. Holding y constant is the partial derivative with respect to x. Okay, so we're going to end up saying this phrase a lot with respect to. So I'm just going to abbreviate it WRT, just so I don't have to write the same thing on the board over and over again. Okay, which is denoted partial f, partial x, or we might also say partial z, partial x, or we might also say f sub x of x comma y, or hopefully never, we may see f sub 1 of x comma y, indicating the partial derivative with respect to the first variable. This is idiotic notation. I hate this, but it is in the textbook. Okay, we're never going to use this. But just in this section of the textbook. The textbook doesn't use it extensively. It just points it out that you might see it in some other arcane place. Okay. All right. But all three of these we will use interchangeably. Okay. Similarly, for the partial derivative with respect to y, holding x constant. Partial f, partial y, partial z, partial y, or f sub y. Okay. So usually we see the derivative denoted by a standard Roman df dx. Here, this is why we changed to a Greek delta to indicate that automatically we know, just seeing this symbol, that f has more than one variable, right? Because we're indicating that we take the partial derivative with respect to x. That implies that we should think of it as a multivariable function, right? If we happen to not know a lot about f, hence the change from the Roman d to the Greek delta. Okay. So let me give you a function, f of x comma y. Let's say it's equal to x squared minus y squared. And we ask you to compute the partial derivative with respect to x of f and the partial derivative with respect to y. How should we proceed? Yeah, exactly. So for example, if we wanted to compute the partial derivative with respect to x, we treat y as though it were a constant. And then the usual rules of differentiation apply, right? So that is to say, f sub x of x comma y is equal to, well, the usual rules of differentiation say that if we take the derivative of an expression that is a sum of things, or a difference in this case, then we can split that up and just take the derivative of each term. Right? So what is the derivative of x squared with respect to x? Yeah, just 2x, yeah. Now, what is the derivative of negative y squared with respect to x? Yes. So with respect to x, yeah. Yes. 0, right? Remember, we're treating y as a constant. There's no term involving x here. So what's the derivative of constant? It's just 0. So this is the entire partial derivative with respect to x. Now, how about the partial derivative with respect to y? Yes. Yeah, exactly. So if you're very observant, this might seem counterintuitive, right? I've written this as the partial derivative with respect to x as a function of x and y, but only in x groups. Well, that's just notation, right? It is a function of y in a trivial way. Y doesn't change it at all. It just depends on x, right? It's kind of a notational thing, but sometimes bothers people. This is somewhat standard, right? We may end up not having any y's or not having any x's, depending on what we do to a function. Right? Okay, good. So mechanically, algorithmically, computing partial derivatives is just like we did in calculus 1. What do partial derivatives mean? What is the interpretation? Yeah. Yeah, very good. Remember, the key phrase here is when we take the partial derivative with respect to x, we are holding y constant. We treat y as a constant. So what does that mean graphically? Exactly what you said. Thank you. But let me make a crude sketch of the graph of f. I'll confess, the reason that we're not doing section 1.8 in great detail is because I took problem. I showed you this website. I'll make an attempt here. So here's the graph of our function from our example. The shape that's commonly referred to as a saddle. Kind of see how this could rest on top of a horse. Okay. So let's put some coordinates on this. Right, here's x straight up will be t, and then coming out of the board y. Okay. So for example, the partial derivative with respect to x tells us the instantaneous, I should say, rate of change along x varying and holding y constant. Okay, so for example, why don't we look at a particular point, okay? Remember in calculus 1, I want to make a strong analogy with calculus 1 here, right? When we compute a derivative, we can evaluate that derivative at a point, and we're told the instantaneous rate of change of the function at that point, right? That is to say, what we usually express, how we express that fact is that we computed the slope of the tangent line to that point, right? So somehow we would like to interpret this as a tangent line to this graph somehow. Now, let me take a second to reiterate something that we talked about last week. F is a function from R2 into R, right? Meaning that its graph lives where? Yeah, in R3, right? Because we add the exponents of the domain and the range to see where we have to draw the graph. And where we draw the graph itself is of one dimension less, right? Making this a two-dimensional object sitting in three dimensions, right? What do I mean by two-dimensional? Yeah. Yeah, that's great. That's a great way to think about it. You can, if we were actually had this object, we could pick it up and squish it down to make it flat. It would just be a plane. Another way, less forceful way, perhaps, is that we can look at any point on this surface. And if we look close enough, it looks just like a plane. This is just like in calculus 1, when we look at any curve and we draw a tangent line, we look really close to the curve where the tangent line is. It looks almost exactly like a line. That's why curves are one-dimensional things, because they can be modeled by a line. This is a two-dimensional thing because it can be modeled by a plane. Around each point, very close, it looks like a plane. So actually, this is what we're trying to do. We're trying to build the machinery to describe explicitly what a plane that looks like this surface in a very small neighborhood. We want to come up with an equation for that using this differential data, the partial derivatives. Okay. Okay. So let's look at a particular point. Let's, for example, consider the point 0. What did I say here? 0.7, 0.5. Then if we plug this point into our partial derivative of f with respect to x, what do we get? $1.4. That is to say, I just plugged x and y into this formula. So 1.4 is, what's the geometrical interpretation of this number? Okay, that's really very close to what we're after. Yeah. Exactly. Again, remember, when we compute the partial derivative with respect to x, we are holding y constant. So in other words, when I evaluate the partial derivative of x, I'm holding y constant. That is to say, I'm looking at, let's again do a very rough sketch of where this point lies on the surface. So I go out 0.7 on x, and then out 0.5 on y. Say it's somewhere like here, right? Okay, so holding y constant fully Y constant means we're looking at the curve where the plane y equals 0.5, the y value from the point, intersects the graph of x. I'm sorry, of f. Okay, so let's add that to our drawing. And again, right, we'll apologize in advance. Okay, so this curve that I've highlighted in squiggle is the intersection of the plane where y equals 0.5 and the graph of f. So what this is telling us is the slope of the tangent line at this point on our graph. That's a terrible tangent line, but I think you know that. Right? It's doing so well. How's that? That's slightly better. Let's tan line slope 1.4. So algebraically, let's just reiterate that f sub x evaluated at 0.5, sorry, 0.7, only 0.5 is the slope of tangent line to the curve f of x comma 0.5, which is just equal to x squared minus 0.25. And all I've done here is plug in the constant value of y that we're considering into our original equation for f. Right? And this gives me a curve, because now I have a function of a single variable. Right? So this value gives us the slope of the tangent line to the curve at x equals 0.7. Okay. I want to put a strong emphasis on this. It doesn't make sense to talk about the tangent line to a surface. It doesn't make sense to talk about the tangent line of a point that lies on the graph of f, right? Because there's a bunch of lines that are tangent. Right? I could come up with an entire family of lines, right? And here's another line that's tangent to the graph at that point. I have to fix either an x or a y, right, to determine a line of tangents. Otherwise, there's an infinite family of tangent lines. What is unique is a tangent plane that touches the surface only at that point. That's what we're building for. We want to use data like this to write an equation of a plane that is tangent, a unique equation of a plane that is tangent to any point on the graph. Okay. So, enough of my rambling. Let's actually compute something. Let's suppose a metal plate lies in the xy plane. And is heated in such a way so temperature is given by the following formula. P of x, y is equal to 100 times e raised to the negative 0.2 x squared minus 0.3 y squared degrees Celsius. Giving you units here. Physically motivated problem, right? Where x and y are in meters. Okay. So firstly, let me ask you to determine the instantaneous rate of change of temperature with respect to x and y. And then furthermore, let me ask you to compute what are these rates at the point 1 comma negative 1. So I made this comment in passing. The usual rules of differentiation apply to partial differentiation. The only thing you're doing different is holding all the variables except the one that you're differentiating with respect to constant. So we take this function p of x, y. For part A, we want to compute the partial derivative with respect to x and the partial derivative with respect to y. Right? That's what I mean by computing the instantaneous rates of change. So partial t, partial x. What do I do? Go ahead. Yeah, so you're saying you can use the property of the exponential function that sum of exponents can be expressed as a product of exponentials. You can do that. I think there's a faster way though. That is only elementary techniques of differentiation. You're not wrong. You can do that. Yeah. Yeah, right. So you shouldn't assign it a specific constant in general. That can be misleading, but when we differentiate, it goes to 0. Okay, so what rule of differentiation will we use to differentiate this function e to the some polynomial? It's required. The chain rule. Yeah, good. Okay, so by the chain rule, okay, first of all, 100 is a constant that's multiplied by the function. So that just stays, right? Okay, so we have 100 times the derivative of e to the something. What's the derivative of e to the something? Yeah, e to the something. Times the derivative of that something, the function that you compose inside, with respect to x. So what is the derivative of this polynomial? Yeah. Yeah, right. So we use the power rule here for x. We bring down the 2. So we get negative 0.4 x minus something that's just a constant, the derivative of which is 0. Good. So I get negative 0.4x. What are my units? Yeah. Not quite. Meters are involved. Yeah. Yeah, exactly. Remember, our temperature is measured in degrees Celsius, and we're calculating the rate of change with respect to x changing, which is in meters. Good. So degrees Celsius per meter. Okay. Now, how about partial t, partial y? Well, basically the same story, right? We use the fact that the derivative of e is itself, and then we use the chain rule to differentiate this exponential polynomial with respect to y. And so we got 100 e to the negative 0.2x squared minus 0.3 y squared times the derivative of this exponent with respect to y. What is that? Yeah, good. Negative 0.6 y. Right? The x is a constant, it goes to 0. Differentiate the y part. And again, you get degrees Celsius per meter. Just a clarifying remark. I'll never expect you to put units on something unless you're given units in a problem. Okay? If you are given units in a problem, then it's important that you include them in your final answer. But otherwise, you don't have to try to fabricate units. Unless, of course, that helps you understand the problem. It can be useful sometimes, but you're not required to do it unless you're given the units at the outset. Okay? So now, how do we determine the specific rates of change at the given point, 1 comma negative 1? Yeah. Yeah, exactly. We'll just take this point, 1 comma negative 1, and plug it into both partial t partial x and partial t partial y. Okay, so that is to say b, and this is just an opportunity to remind you of some notation I hope you're familiar with. This is just from calculus 1, right? Sometimes we take a derivative and then we'll put a vertical bar, and this means we evaluate the partial derivative at the point that is at the bottom of the bar. Okay, okay. So what do we get here? We get 100 times e to the negative 0.2 times 1 squared, okay, minus 0.3 times negative 1 squared, all right, no change there, times negative 0.4 times 1. I would never expect you to evaluate this by hand, but if you plug it into a calculator, what you get is approximately negative 24.26 degrees Celsius per meter. Okay, so partial t partial y evaluated at the point 1 comma negative 1 is equal to, again, 100 to the negative 0.2 minus 0.3 times negative 0.6 times negative 1, which, again, plugging into a calculator, is approximately equal to 36.39 degrees Celsius per meter. Okay, so mechanically, this is not a hard problem. What is the interpretation here? Physically, if we have this metal plate that's sitting in the XY plane. Here's this point. 1 comma negative 1. Didn't draw any axes here, but yeah. put some standard axes here, right? Here's y goes up and x goes across. What this is saying is, yeah, what you're saying, like if you're at this point and you move in the x direction, then your temperature is decreased. Move the y direction, and your temperature is increased. At this point. So let me make a generalization of a theorem that I hope is familiar from calculus 1. And here's an occasion where it'll be helpful if you look at those notes that I sent out about topology. But if not, don't worry, we'll talk about it right now. So, let's suppose U is a non-empty open connected subset of Rn. Sorry, that looks like an H. Rn. And we'll take a function f, which maps U into the real numbers R, with all partial derivatives consistent and equal to 0. I should say equal to 0 at each point. Of U. That is to say, each of the n partial derivatives that we can find of f is identically 0. We get 0 for every input, any point of U. We get 0. Okay? Then the function f is constant on U. Okay, so remember this from calculus 1? If you have a function whose derivative is 0 everywhere, you know that function has to be a constant. Only functions that have 0 derivative everywhere are constants. This is the same thing, but now we're saying that any dimension that you can change in, anywhere you can gauge the change, the instantaneous rate of change, i.e. the partial derivative, if they're all 0, they have to all be 0 to guarantee that the function is constant. Yeah. Well, remember, Rn is a subset of Rn. Rn is a particular subset of Rn. It's a subset of itself. So this is saying something more general. It doesn't have to be all of Rn, but it can. It can be all. Yeah. Yes. Excellent question. So how can we see the xy plane in, I assume you mean R3? How can we see the xy plane as a constant? Somebody describe to me a function that gives you exactly the xy plane. Yeah. Z equals 0. Yeah, great. So for example, Z equal to f of xy equal to the constant value 0 is just the xy plane. Yeah, great. So this is to say a plane in free space, which is parallel to the xy plane, is just a constant function. Right? valued in R. And that makes sense, right? Because you're just at this constant value, nothing is changing. If you take a partial derivative with respect to x or y, it'll be zero. Just an example of what happens in this table. Good. Great. Okay, so what does connected mean? I'll say what it means if nobody knows. Okay, so let's look in R. Our classic situation. Here's an open interval. This is connected. Okay. Here's an example of a not connected subset of R. Take the open interval A to B, and I take the union with the open interval C to D. This is the set I'm considering here. And these two intervals are the set I'm considering here together. When I say this is not connected, I mean that there's space in between them. Right? Again, I have to jump over to from one part of the set to the other. The set has more than one part. That's another way to think about it. Okay. Good. So, yeah. Well, continuity is a property of a function, right? So how do you describe a set as a function? What is span? Yeah, it's this is why we introduce a new term for this. Yeah, it's a separate notion from continuity. Yeah, there's some relation there, but it's best to keep the notion separate for us. So, all right. So, let me draw a quick picture in R2 of the difference between connectedness and non-connectedness. Yeah, our classic example. Here's an open ball. This is connected. Okay. B1, B2, B3. Separate open balls. Yeah. So the set U equal to B1 union B2 union B3 is not connected. Right? Because again, there's gaps between the things that we're considering. Now, having a rudimentary understanding of what connectedness means, why is that a necessary hypothesis for the theorem that we stated here? Here's another way to answer the ask the question. Yeah, go ahead. Yeah, in other words, you can assume a constant value on each of these separate pieces. And the derivative will still be zero, but the function is not constant. It's defined piecewise, i.e. it's not an elementary function. Okay. So in other words, let me write this down. So connectedness is necessary in the theorem, since we could define f of x comma y oh, sorry, I should be explicit here. We could define f going from R2 into R and consider this subset U of the plane and define the function f by the formula f of x comma y is equal to, oh, I don't know, say, why don't we say it's 1 for x comma y in the open ball B1, 2 for x comma y in the open ball B2 here, and 3 for x comma y in the open ball B3. Right? This is not a constant function, but if you take its partial derivatives with respect to both x and y, there's 0 everywhere. That contradicts what our theorem says if we leave out the word connected. So that's why we insist on this notion of connectedness. Okay. Good. So I told you that we would want to ultimately collect all this differential information and treat it as a single mathematical object, right? So the easiest way to do that, there's more than one way to do that, but the easiest way to do that is that we'll just collect all the partial derivatives into a vector value function. So let's say given f, which for u into R, for u a subset of Rn, the vector value function described by nabla f or del f equal to the vector partial f partial x1 partial f partial x2 to partial f partial xn is called the gradient vector function of f. Furthermore, its value at some vector p, an element of u, is denoted nabla f of p hat, or we'll also see nabla f evaluated at p hat. Okay, so this is just verbatim what I said. We take use the subset of Rn, which means that the function f has n variables, x1 through xn. And we can take the partial derivative with respect to each of those variables of f. We want to keep track of all the instantaneous rates of change at one time. Then we'll just organize them in a vector together. Okay? And it turns out that this behaves very much like the derivative from single variable calculus. The main difference being, remember, when you have a function from R to R and you differentiate it, you get a function back that goes from R to R, the derivative. Here, you change the dimensionality of the range of our function, right? We started with a scalar value function, and we end up with a function from U to Rn. Okay. have to be careful about the types of computations that we do, because this is now a vector. Our first intuitively arrived at notion of what the derivative together is has a different dimension than the thing that we started with. Okay, so this is not, it seems like a problem, but we can work around it. Yes. So here we've changed from, we're not using y in this statement because we might have up to n variables. Like y would be x2. Yeah. Good. Okay. So really quick, let's just compute an example before we go, and then we'll talk more about this on Wednesday. When we let w be equal to the following function, x times sine of yz plus y squared e to the z plus x cubed. Then let me ask you to compute the gradient of w. So we don't have much time. So maybe I'll just ask you to think about that and we'll discuss it first thing on Wednesday. But just before we go, outline the procedure here. What do we do? Yeah. Yeah, exactly. So here we have three variables, right? So we're looking at x1 will be x, x2 will be y, and x3 will be z. And then we form a vector function out of those partial derivatives. Okay, great. So have a good afternoon, and I'll see you on Wednesday.